Hello and welcome to Section 11. We'll be talking about the moons and rings in our solar system. And we'll start things off with this brilliant picture, and this is one of the last images Cassini took of Saturn before plummeting into the atmosphere at the end of its life. So to start us off and get us into the mindset, let's just ask ourselves, why do some planets have rings? Here's rings of Neptune, seen by a Voyager as it flew by. What causes a planet to have rings? So with these ideas in our heads, as usual, let's start ourselves off with a nice little simple reading quiz. And this is a bit of a historical one. Turns out, about 2 years after the rings of Saturn were first discovered, astronomers couldn't find them. The rings disappeared. And so the question for you is, well, what happened to the rings? So go ahead and pause the video and come right back when you're ready. So, as it turns out, the rings didn't disappear. It wasn't that the old rings went away and new ones formed by now. And astronomers were not looking at the wrong thing. We discussed in the last section, the discovery of Uranus and Neptune. Basically, the view of our rings vanished. The rings were still there, we just couldn't see them. So let me cut to me on camera and show you what I mean about looking at these things edge on. So let's bring up my model of Saturn here, and I'll have the rings in sight. And this is how we first detected the rings. The ring was in our line of sight. Now remember that Saturn takes about 30 years to go once around the sun, whereas Earth takes 1 year. So the relative positions of how we see Saturn will shift over a couple of years time span. And so when they first found Saturn's rings, we were in this kind of line of sight. But over the few years, as our relative position shifted, all of a sudden we were looking at those rings edge on, and you can just barely make them out. Now wait a few more years and the rings will come back. And so this happens all the time now. We didn't understand that initially when we first saw the rings, but we're just constantly going through these cycles of seeing the rings edge on, where you could just barely detect them, to seeing almost the entirety of the rings. In this section of videos, we're going to go over Earth's moon, where it came from and where we think it came from and what we understand about it. And then we'll break the moons down. We'll compare and contrast the regular versus irregular moons and discuss the geological activity of each moon. Only the major ones. There's more than 200 moons to talk about, and that'd be a very long video. And we'll talk about the rings. One thing we'll notice is that it's all these giant planets that have rings. And at the very end, we'll talk about what gravitational effects happen on a planetary ring system. Looking at some of the pictures of the moon, this is the side that we always see. This is the side that's tidally locked to us. And so it's a face that you can peer up into the night sky and see at any time you desire. And I love having these other images here because these are the faces of the moon that we never get to detect. Far side. We've only recently started putting landers back there. China very recently, 2018, successfully put a lander, I believe it's in this region, and deployed a rover to take samples in this side of the moon. Now, while the feat of landing on the far side of the moon may not sound like this huge ordeal, we've been to the moon before. The technological feat was the technology engineered to have constant communication with the face of the moon that will never see us. How do you have a rover on the back side of the moon talk to us back on Earth? So that's a very wonderful engineering feat. And we can look at the poles. And one thing that I love to point out here is the amount of impact, the amount of cratering that happens on the poles of the moon. Why is that? What is the source of that? So going over bullet points here, we looked at the moon, we noticed it has a density of about 3 grams per cubic centimeter, about 3 times the density of water. And we've gathered together from lunar samples we've taken, observations, that it's almost entirely just this silicate rock. And there are very low amounts of irons and heavy metals. So one of the indications that we have about the origin of the moon is that it was at one point a piece of the Earth, a chunk of the Earth that broke off and flew away. So with that, let's go over into our hypotheses on where our moon came from. There are multiple ideas on what is the origin of the moon, and we're going to talk about the four biggest ones in terms of historical impacts. And while the names here might refer to them as theories, these are theories in just the generic, terrible English language sense of theory. What we really mean is that every single one of these ideas are hypotheses. They are not scientifically accepted ideas. Some of these we can definitively prove are wrong nowadays, but they're still worth talking about and going over together. And we're going to break down what works about them, what doesn't work. The first idea we're going to talk about is this fission theory, and this was proposed by George Darwin in 1879. Yes, son of Charles Darwin. George had an appetite for the astronomy of the universe. So this was the concept. You take this object here, take this proto-Earth, and you have it rapidly spinning around. And if it was spinning too fast, it would fling material out. So let me go ahead and pull up this animation. Go ahead and get this started. So take this proto-Earth, spin around, and get it splitting so fast that the material that became the moon was just launched into space, just globbed out there. And this would do a great job of explaining why the moon is tidally locked to Earth, because it was once a big chunk of the Earth that just managed to float off. Problem with this is that if we do modern calculations about the rotational energy and the kinetic energy necessary to throw this much matter off, it just can't happen in the realm of physics. So this fission theory has been discredited because the math doesn't support it. Our next model for the origin of the moon is called the sister theory. Depending on the text you reference or what resource you use, they'll also be known as the accretion theory. And it's a very simple idea. Take all the material that was floating around the accretion disk. Think back to that nebulous model. Take all that gas, debris, and dust, and just let it accrete into the Earth and moon. Let's go ahead and get this animation. So the concept is that you had the material just floating out there, and over the natural processes of gravitational and minor collisions, one planetesimal got a bit more mass and turned into the Earth, whereas the other planetesimal turned into the moon. So this does a great job explaining why the Earth and moon would be composed of the same relative types of materials, but it doesn't really capture the essence of that angular momentum, the tidal locking of the moon. The capture theory is probably the easiest to conceptually explain. In essence, a moon-sized planetesimal was flying through the solar system and just happened to get too close to Earth. It was then gravitationally locked, it got bounded to this Earth, and trapped. So this does a great job of explaining the tidal locking, just this slow-moving moon getting too close to the planet and having not enough energy to keep going away. Issues with this capture model. While it does get the angular momentum, it doesn't really explain the kinetic energy of this proto-moon. Put this in context. Think of sending a spacecraft to the moon. What do you have to do? You need to launch that spacecraft fast enough to escape Earth's gravitational pull. And then it needs to slow down so it doesn't just fly past the moon, because the escape velocity of the moon is significantly less than the escape velocity of the Earth. So once you have your high-speeding rocket, you need to have retro boosters shoot off to slow your rocket down so that you don't just whiz on past the moon. Well, how does a proto-moon reject all that kinetic energy? What is the retro boosters on a proto-moon to let it slow down enough to be captured? And there is no good explanation. There just isn't a nice way to explain where all that missing energy went when this proto-moon got captured by Earth's gravity. So this theme is that we've noticed that all these different ideas can capture either the angular momentum or the composition, because the capture theory, it's all bets are off of this moon having the same types of composition material as the Earth. So we're going to move on to our last one, our last concept. So we went on to our giant impact hypothesis, and this is the currently accepted model for the moon's origin. In essence, you take this Mars-sized object. It was called Theia by our current models. Theia came in and smashed into this proto-Earth. And what happened out of that is that bunch of debris of Earth got launched out there, flung around, and that material started to circulate, made like a proto-ring around this Earth. And that ring would have accreted into what is now our moon. So this does a great job of explaining the compositional material of Earth and Moon. It's literally large chunks of the Earth just flung out into space. And the tidal locking, it captures the essence of the capture theory, coming in and getting trapped gravitationally. It wasn't that the Mars-sized object just lost all of its kinetic energy and started floating around. It literally smashed into the proto-Earth, and that's where all of its energy went away to. Now, while the giant impact hypothesis that's being depicted here in this artistic impression, interpretation of the event, it's not a widely, universally accepted idea. It's what meets the most facts best. But it's not perfect. We know there are potential errors with this concept. One idea, if we call this Theia the impactor, what was it composed of? And shouldn't the moon be largely composed of what this material is? And so our giant impact hypothesis may have some inklings of failures of the capture theory coming back to it. What this leads us to say is that, yes, the giant impact hypothesis is our currently accepted model. There is still great debate to be had about the origins of the moon. There isn't a perfectly accepted model that matches all of the data, and we're still exploring, still coming up with ideas. And so this next slide I'm going to show you, this is probably one of the most elaborate, crazy ones I've ever heard of, but it has some merit to it. Not widely accepted yet, but still worth talking about at least as a proposed solution of where the moon came from. And in essence, a big nuclear explosion. No, not in the sense of like, good old Americans planting a bunch of bombs everywhere and blowing things up. This would have been a natural nuclear explosion, which, once again, try thinking about that. Here's the idea. You take your proto-Earth, and it's got a huge amount of centrifugal force. This thing is rotating around rapidly. And in principle, what could have happened is centrifugal forces concentrated high amounts of thorium and uranium around the equator of this proto-Earth. Uranium being a radioactive substance, and thorium helps accelerate that radiation process, this fission processes. In this model, in this proposed idea, the amount of thorium and uranium in the crater would have reached this critical density, created this nuclear chain reaction that just obliterated the literal equator of this entire proto-Earth. And that proto-Earth would have then had to pull itself together gravitationally, and some of that material fell back in the Earth, while the rest of it became the new moon.